Okay, let's look at 6, which is a lot like 4 and 5 in that it is really easy. So we have a 12-volt battery which completely charges a 2600 picofarad air gap capacitor. And then the battery is removed and a piece of mica with kappa 7.1 is placed between the plates of the capacitor. Determine the potential difference across the capacitor after the battery is removed and the mica placed between the plates. Okay, pretty easy. So here we go. Let's look at what happens first, which is at the beginning. We've got this battery, and I'm going to call that VA. The battery has a voltage VA. That's the plus side of the battery, and it's hooked up to this battery with a capacitance of let's see. I'm going to call that VA, and we'll call this CA, which is the air capacitance. Okay, so this is when the capacitor is initially being charged up. Okay, so of course it develops a charge Q, negative Q, and since the top side of the battery is positive, obviously we're going to have a higher voltage up there. And so I'm just doing an equation in red because I feel like it. Q, which is the charge that develops in this capacitor, is going to be CB, or the air capacitance times this voltage from the battery in A. And I'm sort of calling this step A. So the fact that A also stands for air on the capacitor capacitance is just sort of a nice bonus. Okay, so then afterwards, this thing is disconnected, and let's see, and then a piece of mica is shoved in. So basically you have this guy, I'll call it that mica, and that gets pushed in there, not slanted but straight, so I know. Kappa 7.1, I think, for the mica. And so I should have finished on my capacitor. So what is the, let's call this B. And so we want to find, first of all, we need to find how that changes the capacitance, CB, and then we need to figure out what the voltage is afterwards, and that's going to be VB, the voltage difference between here and here, and this is VA here, sorry. Okay, so what stays the same, really, is usually the first question you want to answer. When you have something tricky like this, the first thing to look for is what stays the same. Well, charge is going to stay the same, right? Because once you've disconnected this guy, if you cut this wire here and this wire here, where's the charge going to go? Ain't going nowhere. So you have Q and minus Q there. And this is plus Q, just to be clear, but, you know, whatever. Okay, so we shoved this thing in. And how does a dielectric, putting a dielectric in, change the capacitance? Well, the capacitance with the dielectric, which is what we're going to have in figure B, is just the dielectric constant times the capacitance without, which is what you had in A. So that's pretty easy, right? And then it gets easy, you know, well, this part gets easy because now to find the voltage across the plates after this mica is inserted, you just go Q equals, and then you apply Q equals CV to the after stage. So here's your voltage across the battery B, here's the capacitance with the mica, and it's all good. And so really what this amounts to, since charge is conserved, you take this equation and this equation, set the right hand sides equal, and you get CA VA equals CB VB. And probably what I should have done was done this little plug-in first, so we'd have the kappa CA, but I'll do that now. So CB is kappa CA, and then we have the VB there. So what you're going to get, I think, what do we want? We probably wanted VB, right? VB would be the potential difference across the plates after the battery is removed and the mica is placed between the plates. So there we go. So we just take this equation here, which I am outlining in baby blue, and we let's go back to, ooh, here's kind of like a slate blue thing. Let's try that out. So we just solve this one for VB, and VB equals kappa times CA. No, I'm sorry, that's wrong. I've got my fractions wrong. I'm trying to be too clever. VB equals CA VA over kappa CA, Or, even simpler, it just equals VA over kappa. So this is kind of interesting. Let me just write the whole thing there. VB equals VA over kappa. That's kind of interesting because actually it turns out that what the original capacitance was doesn't matter. All that's going to happen is you're going to take VA, and no matter what the initial capacitor was, shoving mica in there will have the same effect. It'll increase the capacitance by a factor of 7.1, which means if the charge stays the same, the voltage will decrease by a factor of 7.1. So for this particular case, I mean, if you really want to, if you can't divide 12 by 7.1 yourself, I'll do it for you. Man, crap. Maybe you're better off learning how to do it if you can't, because I'm not going to figure this calculator out. Oh, clear. There we go. Okay. 12 divided by 7.1. It is 1.69. Yeah, I guess we'll stick with that. So, this voltage here, which is what we wanted to find, this is our, whoops, that's our answer, equals, equals 1.69 volts. And that is our answer. Pretty easy.